And so previously, we saw frictionless situation, but now in this problem, the student is going to glue a piece of felt to the top of the car, and we did not do that in lab today, but then flips the car upside down within the launcher so that the car is launched, and here we go, here's our new stuff. It slides to rest due to the effects of a constant frictional force. Friction is what kind of force that does what kind of work? Non-conservative. So we're headed back to that work energy theorem. Non-conservative work equals what kind of changes in energy? Do y'all remember? It's one of the three versions of our theorem. What kind of energy changes with non-conservative work? That would be for conservative. Change in mechanical, which, if we define our system the good old-fashioned way, spring, earth, object, then this mechanical is going to be changes in kinetic and changes in potential. Now, let's talk subscript. In this example, again, this one's an extension of the lab type. There's no height change on this glass tube with the car. It's going across a horizontal track. And so I'm not even going to talk about gravitation. So I'm going to call this one, it's elastic change in potential. I guess if you want to feel complete, you could include gravitation, but no height change. So no change in gravitational potential energy. And it says the student once again is going to hypothesize that the sliding distance, and they specifically say capital D, not a generic lowercase d. So you got to be mindful of these very defined variables. The student hypothesized that capital D is directly proportional to the compression distance again. First question, write an equation. Now here's where we need to edit. Okay, the original NIMSY actually said V and D, but they haven't set us up for V, and the answer key all addresses X. And so go on and change that to a X and D. This compression distance with the sliding distance. Both are distances, be careful. And it says you can include constant quantities and then use the equation to evaluate, correct or incorrect, the student's hypothesis. Again, they hypothesize that the sliding distance is directly proportional to the compression distance. So let's spend some time with our work energy theorem here. And so the non-conservative force doing work on it as it slides across, remember we've got that felt pad, it's going to slide to a stop. And so it'd be the work done by friction. And then the kinetic energy change, let's take a look at final minus initial. Well, initially, when we're fully compressed and you let go, what's the initial speed? 0. So initial kinetic energy would be 0. And then this one has friction. It's going to slide to a rest. So final kinetic energy will also be 0. So it's about where you start and where you end. It's going to be 0 on both of those. What about elastic potential energy? Well, in the beginning, when we're fully compressed, we hopefully recognize you have stored elastic potential energy. So we will have that initial. What about final? When it leaves the spring and slides to a stop, is there any compression? Is there any stored elastic potential energy? No, the spring is not compressed or stretched. And so the final version of that would equal 0. Moral of the story, the work done by friction is going to equal a negative elastic potential energy in the beginning. Okay. So now breaking it down, work done by friction, we can plug in what? Work equals force times distance. And so force of friction, now be careful here, generic little d, but they said the sliding distance is a capital D. Give them what they want. And true story, friction is going to do what kind of work? As it moves forward, friction is going to work back. So technically it's going to be doing negative work. And I bring that up because what's going to happen to our negative signs on each side? It should cancel out. Plug in that 1/2 kx squared. Okay. And so now identify the constants. So they told us up above that the frictional force was constant. And so you could do mu Fn, but they tried to make it easier on you. They said it's a constant force. And spring constant is constant. And so now we're focused on D and the compression distance. The student claims that X and D are directly proportional. True or false? False. So the student is incorrect. So let's correct them. X squared is proportional to D. Okay, you can't forget the square. And so what does that mean? When you double the compression distance, how far does it go? It goes 4 times the distance. Okay, that is not proportional. Proportional, direct proportional, it would mean double, double. But here we have a double quadruple. So it's not X versus D, but it would be X squared versus D. Good deal? Okay, one more little part for this question. On page 27, we get our last part. They give us a sample data table. It says, after performing several trials, the student creates a data table as shown. Does the data support the student's hypothesis? Again, the student hypothesized that that stretch distance is proportional to that sliding distance. That's what they hypothesized. And so if we look, so again, it's that double, double. Look at your data. Can you find 2 data points that have a double compression distance? You got a couple options there, but what if we pick 0.02? Double would be 0.04. And so here you have a double. Look at your sliding distance. Do we get a double? No. So this one is a quadruple if you look closely, but it's not a double. And so does the data support? No. Explain your reasoning. So here, if the student was correct, and so if D and X were proportional, then doubling the compression distance would double the sliding distance. But in the table, doubling the compression yields 4 times the sliding distance, which actually agrees with what we said earlier, that D is proportional to X squared. We said double squared was quadruple, and here the data supports that, okay? So it's actually good data, just the student made the wrong hypothesis. Make sense? And again, not all of your May exam lab-based questions are going to be, is the student right or wrong? It's not always going to be write out a procedure. Maybe they give you data and have you linearize or have you do something with it, okay? Questions on F2. We'll do F3 next class, but to end today, and I think we have time, head back to page 14. Last class, we did that pendulum simulation. We didn't have time to do this pendulum workout problem. And so we've got this pendulum mass on the end of a string. It's called a bob. Hi, Bob. So page 14, it might be the other side, 13. I know that pages got flipped when I copied paper copies. It's held at rest by two strings. One makes a 30-degree angle with the vertical. The other is a straight horizontal string. And so now, AP loves to cut strings, y'all. They're going to cut the horizontal string. Well, what's going to happen to Bob? Swing down. Okay, you see that semicircular motion, but there's a couple special places. Right now, it's at a high point, right? It's at a high point. And so at this highest point, what kind of energy do we know it to have? Do you remember? Potential energy. And if we cut the string, it's going to be released from rest. So kinetic energy at this point would be 0. And it's a string, not a spring. And we'll assume it's not a rubber band. So we won't even bother with elastic potential energy. And then it's going to swing down to a low point, which also is dead center of your pendulum, back and forth, back and forth, back and forth. What is this middle-ish point? Equilibrium. So here at equilibrium, at the low point, well, if this low point is as low as it's going to go, what number can we give it? 0. So how much gravitational potential energy does the bob have at the low point? 0. So where did it all go? Neglecting any air drag or friction, now it's all in the form of kinetic. And so we will have kinetic energy at the low point. Turns out it's going to be a maximum too. Okay? And that's what they want us to solve for on this problem. What is the speed at this low point? And so using conservation of energy, and so the potential energy we start with is all going to transfer to kinetic energy at the bottom, where we're going to end. Not that it stops there. We're just like pausing our simulation right there. And so mgh equals 1/2 mv squared. We will be solving for v. What do you notice happens? Mass cancels. Now they did give it to us. They said in the picture 1.8 kilograms, but it's not needed when you're solving for the speed here. And so to solve for v, multiply both sides by 2, take the square root. Simple enough, yes? Uh-oh. What do we plug in for h? The height change. Is it 2.3 equal to the length? No. But do you see a right triangle? Can we do some trig? Now be careful, height is not in the triangle. Let me zoom in a little more. Okay, the height that we want is just outside. It's from the low point to the high point. Well, maybe I label this side of that right triangle with a Y. You can pick whatever favorite letter. How could I put Y and H together? What would that be equal to? It would equal 2.3, the length again, okay? And so our length would be that Y plus H. And so a little bit of trig, we know the length is 2.3 always. And so how do I find that Y? Well, someone grab a calculator. You'll use what trig function to find that adjacent side? Cosine. Turns out it's 1.99 we'll just call it 2. And so the height change is actually going to be 0.3. And that's what you'll plug in to get your speed. And so I don't remember what it is. Anyone got a 2.48? Is that what you said? Okay, so 2.48, I'm just going to go 2.5. Would be the speed at the bottom, okay? Questions on the pendulum? Okay, so next time we'll actually continue with this question and we'll find the maximum tension at that lowest point. Do a little bit of review. We got circular motion and forces still here. And then we'll keep going. Maybe the problem below, we'll go back and hit some NIMSIs. We'll work on some concept questions, okay? And so next class, your warm-up is gonna be get with your group, compare spring constants, fix any mistakes maybe that need to be fixed, all right? We'll turn the lab in next class. Y'all have a great day.
So
Hold on.